Hello viewers, welcome to the channel Essay Easy Learning. Today I start with a theorem. So let's begin. The theorem is, let P be a prime number. If P divides A square, then P divides A, where A is an positive integer. Let's prove. At the first, let us factorize A, which is a positive integer, with some prime numbers. That is prime factorization of A. So let us consider A equal to P1, P2 and that Pn. We consider A is a positive integer and prime factorization of A, that is A equal to this, where P1, P2, Pn all are prime numbers. Okay, but not necessarily distinct. Maybe there are many prime numbers, they are equal, because if we consider an example, that is 12. So we can write 12 as the prime factorization of 12, that is 2, 3, 2. So 2, 2. So obviously prime factorization of any number, there are not all the primes that are not necessarily distinct. Maybe there are equal prime numbers. Okay. So they are prime numbers and not necessarily distinct. So therefore, if we consider A square here, so this is A and this is A. So if we multiply A into A, that is A square. Okay. Now given that P divides A square, that means P divides this. Now they are prime numbers. So here P1 into P1, that is P1 square, P2 square and hence Pn square. So A square equal to this. And given that P divides A square, so by the fundamental theorem of arithmetic, it follows that P is one of the prime factors of A square, because P divides A square. Since P divides A square, so obviously we can say that P is one of the prime factors of A square. Now, using the uniqueness part of the fundamental theorem of arithmetic, obviously we realize that only prime factors of A square, that are P1, P2, Pn, they. Only prime factors of A square are this. So obviously we say that P is one of this. Okay. Now we conclude here A equal to P1, P2, Pn. Prime factorization of A can be written as this, where P1, P2, Pn are prime numbers. So since A equal to this and P is one of these, so obviously we can say that P divides A. Right? Since P is one of the term P1, P2, Pn, so obviously P divides A, because A is written as the product of P1, P2, Pn. So we prove that P divides A. The next theorem is root 2 is irrational. We have to prove it. Okay, we know that rational number always can be written as P by Q form, where P and Q are integers and Q not equal to 0. Now we have to prove that root 2 is irrational. So let us assume that root 2 is irrational. Whenever we conclude root 2 is rational, so obviously root 2 can be written as P by Q form. So root 2 that equal to P by Q form. This P and Q are integers and obviously Q not equal to 0. Okay, now we conclude P and Q are integers and Q not equal to 0. So obviously suppose P and Q have a common factor, that is other than 1. P and Q have a common factor. Assume that common factor other than 1. then obviously we divide by the common factor to get that root 2 that equal to a by b. Okay, that is if we consider that p equal to 2a and q equal to 2b. If we write an example p by q, that p equal to 2a and q equal to 2b, and we get the common factor other than 1, that is 2. So obviously 2 cancel out and root 2 can be written as a by b form. Okay, so from this we can write a equal to b root 2 cross multiplication. Now square the both sides, that is a square that equal to 2b square. Okay, from this a square equal to 2b square. So from this we can conclude that 2 divides a square. Obviously 2 divides a square because a square is written as 2 into b square. So obviously 2 divides a square. Okay, now by the previous theorem we conclude that if p divides a square, then obviously p divides a, where p is a prime number. So here 2 is a prime number. So if we say that 2 divides a square, so obviously this implies that 2 divides a from the previous theorem. Now 2 divides a. So obviously from this we can write a equal to 2c. C is any integer. C is any integer. A equal to 2c because 2 divides a. Right? Okay. Now a equal to 2c. We substitute a equal to 2c in here. So a equal to 2c, there is a square. So 2c whole square. So 4c square, that equal to 2b square. So obviously 2c square that equal to b square. We divide by 2 both sides. So if we consider 2c square equal to b square, so obviously we say that 2 divides b square. And by the previous theorem 2 divides b. Right? So 2 divides b. Therefore a and b have at least 2 as a common factor because 2 divides a we get, and now we get 2 divides b. So 2 divides a also, 2 divides b also. So obviously a and b have at least 2 as a common factor. Right? But this contradicts that a and b have no common factor other than 1, because in previous I say that root 2 equal to p by q, that, and pq have common factor other than 1, and we divide the common factor and we get root 2 equal to a by b, where a and b are integers, but here GCD AB that equal to 1. That means there are no common factor other than 1. And now we get that a and b have at least 2 as a common factor. So obviously this contradicts the fact. Okay. So we conclude that root 2 is irrational. Since we assume that root 2 is rational, so we get a contradiction. So we say that root 2 is irrational. Okay guys, thank you for watching.